So we were doing the motor control circuits. So we have discussed motor control circuit for the DC machine. We have discussed this circuit, that is shunt motor starter with voltage sensing element. The same circuit made with current sensing relays, and we made with off delay timer or time delay contacts. The same circuit, shunt motor starter circuit. We have done also series motor starter circuit with the current sensing relay and with holding coils. Relays with holding coils. These are all examples. That doesn't mean that the circuit should be exactly like this. It is like solving any problem. So we can have other logic also. Now next main important motor used in the industry is induction motor. So this is basically the automatic starter for a DOL starting. DOL starting means direct online starting. So this is the starter. Basically, we have in our household application, that is household application, the pumps are single phase motor, but the same thing, that is only a start and stop button is there. So basically we have a stop button and the start button. Stop button is always a normally closed push button, and the start button is a normally open push button. So this is the main coil. So main coil M will have contacts in the power circuit, and in the control circuit it is the holding contact which will bypass the push button. So if we press the start button, this main coil is excited. So this contact will close, the motor will start. Only we have the overload protection. So these overload contacts are normally closed. Whenever there is a overload, this overload protection will operate and this will contact will open. Another operation which is there is the under voltage, because if the voltage drops below some value, this coil is deactivated. So the motor will cease to rotate, and as soon as the circuit is disrupted, this has to be started again, because it won't start by itself because this portion is open. This was the dual starter. So next is the for wound rotor motor. Now for wound rotor induction motor, the advantage is that we can introduce resistance in the rotor circuit. That is the advantage, and it is normally done to have high starting torque. Otherwise, the squirrel cage variety is more sturdy. Now, this is one of the circuits. Here, this is the resistance in the rotor circuit, which has to be cut off. Now, initially, when we press the start button, this M coil will be excited. So, this contactor will close and the machine will start with all the resistances in the rotor circuit. So that rotor is shorted through the resistance. So it will start with a high resistance. So starting torque will be high. Now here, this this contact, this is the this figure is not very clear. 1TR, this relay is in contact with the normally closed contact of M. Now, as soon as M activates, this contact will open. So this is a time delay relay. So the time delay is introduced when it drops off. So normally when it is excited, this contact, which is normally closed contact of 1 TR, is open. But as soon as this contact opens, this relay will drop off, and after a certain time delay, this contact goes back to its normally closed form. So when it contact closes, so this 1A is excited. When 1A is excited, this will close its contact in the power circuit, so shorting this portion of the resistance. And in the control circuit here, we have a contact of 1A. Now, as soon as 1A, this 1 TR is closed, 1A is excited. So as soon as 1A is excited, this contact, which is a normally closed contact of 1A, will open. So when it opens, this relay to TR will drop, is unexcited. So when it drops off, it introduces some delay, and this contact will go back to its normally closed form after that time delay. So as 1A is excited, this will close, and but this will close after certain time delay. So after certain time delay, this relay 2A is excited. When 2A is excited, these contacts will close, and this portion of the resistance are shorted. And in the control circuit, this contact of 2A, which is normally closed, will open. So when it is open, this relay 3TR is unexcited. When this 3TR is unexcited, after certain percent time delay, this will go back to its normally closed form. So 3A is excited. So this contact will close. So as this contact closes, so all the resistance is cut off. So when it is running, these are not carrying current. These relays are only carrying current. So on a running condition, we will have no resistance in the circuit. So this is for wound rotor starting. Now, this is again the wound rotor starter with the frequency sensing relay. The same thing. That is, we have resistance. Initially, we have all this resistance in series with the rotor winding. Now we have to cut off the resistance in series. In the previous one, we have used time delay relays. Here, frequency sensing relays are used. So these relays are set. It is sensing the frequency. So frequency of the rotor circuit, and as we know that as the rotor speed of the rotor increases, the frequency of the rotor circuit changes, and these relays have different settings. So when we press the start button, so this M get excited, this contact will close, the motor will start with all the resistances in the circuit. Now, at particular frequency, where for a particular speed of the rotor, this 1A part is activated. When this one is activated, this will close this contact here. So 1A is energized. So this will close 1A contact in the power circuit. So this portion of the resistance is shorted. Now 1A has also a contact here in the control circuit. So when 1A is excited, this will close. But however, this is open, this will be excited only at a particular preset value. Here also we have contacts like that. Once M is excited, then M here is closed. Then only this relay is relay comes into play. Now again, when 1A is excited, this contact will close, then only this relay will sense the voltage here. So depending on its setting, it will be excited at a particular corresponding to a particular frequency. So this contact will close. So 2A is excited. So 2A, this contact will be closed, and also this contact will be closed, activating this relay, and this contact will be closed. Now this relay will close its contact at a particular corresponding to particular frequency. So then 3FR will close. So when 3FR closes, 3A will be activated. So this contact will close. Then there is a contact in the control circuit here and a control circuit here also. This contact also will close. Then this 4FR will close its contact at a particular frequency depending on the setting. When this closes, this 4A will be activating closing these contacts. So the machine will run with no resistance in the rotor circuit. Now I have discussed a dual starter, which was for one direction only. Now there can be some load where we require the speed reversal. Now we know that for speed reversal we have to interchange two phases. That also can be done. This dual starter has a speed reversal provision. Now these forward contacts are connected here. Now reverse contact, you can see that these are same. Now for reverse contact, this phase will be connected to this, and this phase will be connected to this. So these two phases are interchanged. So the machine will run in the reverse direction. Now here what we have, normal stop push button. Now this forward button is a two-way switch. So in if we want to run the machine in forward mode, when we press, then this contact will open and this contact will close. Now when this contact closes, what is the path? You can see this is closed. This is a normally closed path. So through here, then this is normally closed. So forward coil is excited. So that will close the forward contacts in the power circuit as well as this forward contact. This is equivalent to the holding contact what we have across that main coil M. Now what happens if we press the stop button? If we press the stop button, the circuit is interrupted, control circuit, so this contact will open. Now what happens if we press the reverse button? If we press the reverse button, then also the forward path is broken. That is forward path, this was the forward path. So if we press the reverse button, the forward path is broken, but this path is now closed. Now what is the path? Then this, through this, then the reverse contact will, reverse relay will be excited. So the motor will now run in the reverse direction. So the speed can be reversed without stopping. That is, without pressing the stop button. If we press the forward button, the forward connection is disconnected and it is connected in the reverse direction. So this is the dual induction motor starter with provision for speed reversal. Here also normally it is provided with overload protection. Now this is a induction motor starter with auto transformer starting. The induction motor, we know it is a very common starting is auto transformer starting. Now this, if we, this is the main supply. So this from here, this power is taken. This is the control circuit, and this is the main power circuit. Now here we have the start button. If we press the start button, then what which circuit get powers from here? This is closed. These two contacts are closed. So this V is excited. Coil V is excited. This is a timer. T is excited, and in this circuit also, this coil U is excited. In on this, however, we have, you see that if we go here, this now we have some delays introduced because we have a timer. So if when V and U are excited in this circuit, this contact will close. So when this contact close, this is basically an auto transformer. So it is to the motor. So what happens? This is to the auto transformer input, and the motor supply will go from the auto transformer output. So motor will start from the auto transformer. Now what happens? We have a timer here. So according to the setting of the timer, after certain time, this T, this is a normally closed contact, will open. This T will open, this T also will open. So these coils V and U will be unexcited, so these contacts will close. And here we have this, when this U is unexcited, this is a normally closed contact of U, so this will go back with normally closed form. So this is normally closed, so this circuit is excited. So W is excited. When W is excited, then these contacts will close. So the motor will get full voltage supply from the supply. Now, however, you can see that for entire process, stop button must be pressed. Otherwise, the circuit will get disconnected. So we have this indicator provision here. When W is excited, this will close and this lamp will close. When this lamp close, then only says that the total starting operation is complete. So we can remove our hand from this start push. The circuit will normally go like this. This is a normal question. So this is the auto transformer starter. Now both this and this circuit over there, that looks slightly different because the different conventions have been used, but both are correct. This because they are taken from different books, so they follow different conventions. So these figures are I have done that is taken from COSO. This is from Pication's book. So both are correct, only that they have shown different conventions. The circuits are the same. Now, we have just explained a few control circuit. Next, whatever we have in the syllabus, this is first particularly we will have the motor selection criteria, then the temperature rise equation, the transient equation derivation, then duty cycles, etc. Now, before going to other calculation, I will define the duty cycles. Now, what is the duty cycles? Now, the motor rating, what we select, will depend on the duty cycle. That is, say if the maximum load requirement is 2 kilowatt, then if it is required for a continuous period of time, then in that case we select a motor of 2 kilowatt. But if it is such that the motor is required to run for a very small time period, then even if the load requirement is 2 kilowatt, we can go for the motor rating which is slightly less, and we can overload the motor, because ultimately what is important is the temperature rise, and the rating of the machine is decided by the temperature rise of the machine. So if it is continuous duty, then we have to choose depending on the power rating. But if it is an intermittent duty, we can choose there are methods to calculate. We choose a machine of lower rating, which is lower than the maximum rating, but which will be able to deliver that power for a short time period. So according to Indian IS, that 4722, there are different, this I'm skipping, duty cycles, with some 8 duty cycles are defined. These 8 duty cycles are defined. So what is the duty cycle? S1, it is the continuous duty. S2 is the short time duty. S3 is the intermittent periodic duty. S4 is the intermittent periodic duty with starting. S5 is intermittent periodic duty with starting and breaking. S6 is the continuous duty with intermittent periodic loading. S7 is continuous duty with starting and breaking. And S8 is continuous duty with periodic speed changes. So what is important for this? So what is the continuous duty? Continuous duty, if duty is continuous, then the load will remain constant. This is the duration N. Now, as the load is constant, so losses also will remain constant, because the motor losses, mainly it is the fixed losses and the variable loss. So in both the cases, we are considering the supply voltage to be no voltage variation is considered. So the core loss is constant. I square loss is also constant. Now, if the loss is constant, then how the temperature will rise? The temperature rise characteristic of any motor will, we will derive the equations also afterwards. It will be an exponential curve like this. So for initial portion, the temperature will rise. This is the ambient temperature. Then after a certain time, what will happen, because the losses manifest itself as heat. So this heat is dissipated to the atmosphere. Now, when it happens that the loss in the initial state, whatever the heat generated, a portion is utilized to raise the temperature of the motor, and the portion the rest is dissipated to the atmosphere. Then at a time it so happens that the temperature becomes more or less stable, and whatever heat is generated is dissipated to the atmosphere. So we will have a exponential curve. Though actually ideally this flat portion will be obtained at infinite t is equal to infinity, but normally this when the temperature difference is say 1 degree is over a long period of time, then we can consider it to be stable. Now, so normally any normal design motor will take around 2 hours or more to attain this maximum temperature. The motor, the insulations are selected based on this temperature. So if when the load is such that it requires to be driven for a quite long time, so that the temperature attained by the motor will approach the maximum. So then in that case, the motor has to be selected depending on this maximum load requirement. This is the continuous duty. So theta max is the maximum temperature attained. N is the operation under rated condition. That is a time period for operation under rated condition. This is S1. Now, what happens to short time duty? Short time duty means, say that the load amount, this kilowatt, if it is, that is the same, but the duration is small. N is quite small. So when the load is constant, the losses are also constant. Duration is small. So what happens to the temperature rise? The same curve, the temperature will rise, but actual curve was like this. So, but the load is disconnected here. So temperature will not rise beyond this point. So if we select the motor based on this old power rating, then what will happen? And if we operate the motor for this time period, so the temperature will rise up to this. So we will never attain this theta max. So again, it will drop. So then we are actually not utilizing the total motor capacity, because so what we did, we select a motor which is of lower rating, so that this it's within this time period it will attain the temperature theta max for which its insulation is designed. So we can go for a smaller power rating, so that will save our cost. So this is the short time duty. It is that duration is defined in such a way that the time is such that the motor of kilowatt, this amount of kilowatt rating will never attain the maximum temperature. So we select a motor which has a lower rating, so that it is overloaded, and so this curve was for the full load. So if it is a overload, power losses are more, so this portion will be steeper. So the motor will attain its maximum attainable temperature. This is the short time duty. Next one is S3, short, it is intermittent periodic duty. The same short time, but it is repeated as the time R. The same cycle is repeated. So temperature, what happens to the temperature here? It will increase. Now in between it will decrease. Again it will increase. So this is a steady state. This way the temperature will grow. Now what is the difference between the short time rating and periodic rating? In short time rating the temperature is decreasing, but this of time is large enough to bring down the temperature to the atmospheric temperature or ambient temperature. Here this duration is not enough to bring the temperature to the ambient temperature. So that, because here also we can have another pulse here, but then it is not called intermittent duty, but because it is off for a long time. So this is the short time duty. This is the intermittent periodic duty. So So we define certain quantity. N is the operation under rated condition. R is the at rest or de-energized state. Theta max, maximum temperature attained during the duty cycle. And cycle duration factor is N by N plus R. N plus R is the cycle duration factor. Now, in both this is intermittent periodic duty. Then next one is S4 is intermittent periodic duty with starting. That is, we always start the motor. With starting means then, say if the load is a high inertia load or a particular type of load which requires considerable starting time and starting current. That is, if starting time is very small compared to the duration cycle, then we definitely do not consider it separately. But if due to high inertia or other reason, the starting time is comparable. From here you can see this is the starting time, which is comparable with the running time. So then we have to consider it separately, because during starting there will be high current, so losses also will be high, so temperature rise will be high. So here if we draw the load curve, this is the load curve, this is this power requirement during starting will be high, then this is the normal running, this de-energized state, then again the cycle is repeated. And what happened to the losses? The losses during starting will be quite high, because losses that I square R loss, it is proportional to I square. The current is higher for starting, so loss will be quite high. So this is the loss. This is slightly decreasing here because you know the current will not be constant. The starting current initially large, it is a transient, it will decrease. Then this is a normal running, and this is a de-energized state, so no loss. So for the temperature rise, initially for this type there will be sharp temperature rise. This is motor is running, but it will be slightly, temperature will slightly drop from here because there is a large difference between the loss during starting and the running. So then the energized state, it will fall again the same thing is repeated. So this is for intermittent duty with starting. So here also we defined D is the starting time, N is the operation under rated condition, R is rest or de-energized time, and theta max, maximum temperature attained. Cyclic duration factor is D plus N by D plus N plus R. So this is for S4. In S5 we will have braking also. That is, at this point it is de-energized. Here we do not have any separate braking, just de-energized here. But if we have electric braking, then there will be current flowing and there will be losses also. So the power is fed back to the supply. But from the point of view of motor losses, there will be losses and there will be heating. So here, if we consider the motor with starting and braking with intermittent loading, so this will be the load diagram. So this is starting, this is continuous duty, then this is braking. And for the losses will be high during starting, constant during constant load operation. Then for during braking it will be higher, these losses will be higher. So this is the electric loss. So what happens to the temperature rise? Temperature curve will be like this. In this region it will increase, then decrease, then increase more sharply. Here losses are larger, then it will drop, then the same thing is repeated. So here the cycle duration factor is D plus N plus F. That is D plus N plus F divided by D plus N plus F plus R. So this is S5. Then we have S6. S6 is the continuous duty with intermediate periodic loading. Now In continuous duty means the difference between this one and the intermittent loading is that here it is de-energized, the motor is disconnected. But if so happens that motor is not disconnected, just running at no load condition, then the load curve will be like this because it is no load. But if we look at the losses, loss curve will be like this. It is no load, so losses will be small, but it will be there. So the temperature rise curve looks almost similar, but this drop will be less here because there was no losses. Here there will be losses. So if it is S6, the curves will be look like this. So here the cycle duration factor is again N plus V, where V is the operation on no load. Next one is S7, means starting continuous duty with starting and electric braking. That is some similar to this is, you can see it is it can happen in some processes, that is it is not disconnected, it is the continuous duty, it is the portion it is started, then continuous duty, then there is a braking, then again a starting like this. There is no gap between this. There might have so happen that there can be a rest period with no load operation for a small time. It depends on what load it is driving. So if this is the curve, then what happens to the loss? The loss in this region for braking and starting, that will be large. It is constant here. So temperature rise curve will be like this. So and the final one is S8. S8 means continuous duty with variable periodic speed changes. In the previous one, I have considered constant speed. But say for steel mill or paper mills, the same machine, the speed requires difference. Say for steel rolling mills, for every and each and every pass, the speed should be different. So here, this is a starting, then running at a particular speed, then there is a braking. So that speed will reduce now. After this, it will again run with a constant load for certain others lower speed. Then again a braking, then again a drop in speed, again starting. So it will again go to the higher speed. So this is the total cycle which is repeated. So what happens to the losses? During the braking, there will be high losses. During the starting, there will be high losses. Then there is a constant loss. This is higher power, so this is a constant loss. Then this is braking, higher losses. Then this is a constant loss, but lower power rating, so loss is also low. So this will be the electric loss distribution. Temperature rise will be accordingly. Here it will rise, then in this region decrease, then again rise and decrease. So it will go on like this. And the speed curve, it is added additional. So this portion of speed is maximum. In this starting portion, basically, it is accelerating. So speed is increasing from here. This is constant. Then braking here. That means decelerating here to some speed. Again decelerating to this speed. Again we will have acceleration or starting. So this is the speed profile. So F1 and F2 are braking. This F1 and F2 are braking, electric braking. T is acceleration. This time is acceleration. N1, N2, N3 operation under rated condition with different speed. Theta max, maximum temperature attained during duty cycle. So duty cycle duration factor is D plus N1 divided by the 2. different with respect to different. One is d plus n1 divided by d plus n1 plus f1 plus f2 plus f2 plus n3, or we can have f1 plus n2. For this cycle, it is f1 plus n2 divided by the total time, or f2 plus n3 divided by the total time. So there is a cycle duration factor. Now what is important is that from here you can see that depending on its temperature rise, the motor should be selected, because the motor rating actually ultimately is decided by its temperature rise. Now in electric motor, main two losses are I square R loss and the core loss. Now the core loss depends on the voltage and frequency, and the I square L loss depends on the current. So as long as voltage and frequency remains constant, core loss is constant, and the I square L loss will vary with current square. Now, depending on that, what is for continuous duty, what is the total loss that will be manifest as itself as heat. The temperature rise of the motor is calculated, and deciding on the temperature rise, the insulation is selected, because insulation is temperature sensitive. Now, what happens if we select a motor, as I have told that, say for 200 kilowatt load, but it is intermittent duty. So if for 200 kilowatt load, if we select a 200 kilowatt motor for intermittent duty, so it will never attain its maximum temperature, because the curve is this one, the first curve, this one. So this temperature it will attain if it is running 200 kilowatt load for say around 2 hours. This time requirement is quite large. So if it is run for say 15 minutes up to this, only this will be the temperature rise. So that motor is not utilized properly. So we select a motor which has a lower power rating. So it is overloaded. As it is overloaded, this curve will be steeper, sharper like this. So within that small time period, it will attain the maximum temperature. So we can utilize the capacity of the motor. So we have to decide, we have to have certain methods to calculate the motor ratings. So motor ratings, I am not starting motor rating calculation. This is we will go for motor rating calculation next day. Now we will have a next class on next Tuesday, the same time, 3 o'clock. Okay.
Okay, ma'am. Okay, ma'am. Okay.